Hello everybody and welcome to the homework helper for section 3.1. We're going to be looking at this first section here. We're going to be comparing additive and multiplicative patterns, which is a very, very fancy way of saying additive is a fancy way of saying arithmetic, and multiplicative is a fancy way of saying geometric. And all of that is also just a very fancy way of saying linear and exponential. Okay. And just as a quick reminder, the general form for linear is going to be f of x equals our n sub 0 plus our common difference times x, whereas for exponential, it's going to be f of x equals our n sub 0 times our ratio to the x power. Those are our general forms of those equations. We've touched on this before, but it's been a while. It doesn't hurt to refresh it. So what we're going to be doing here is we're going to be looking at these different sequences, and we're going to try to identify whether or not they're arithmetic or geometric. So we're going to start with this first one. We see that we go from 2 to 4, okay? And so that means we're doing either one of two things. We're either adding 2 if it's going to be linear, or we're multiplying by 2 if it's going to be geometric. So let's see what happens here. Then when we go from 4 to 8, well, we're either adding 4 or still multiplying by 2. Okay? And then from 8 to 16, we're either adding 8 or multiplying by 2. So clearly what we're doing at each step is we're multiplying by 2. So if we're multiplying by 2, this would be 32 times 2 would be 64. 64 times 2 would be 128. 128 times 2 would be 256. All right. So we know that the type of sequence is it's going to be multiplicative, or we'll just call it geometric, because that's a much better word, geometric. Let's see if I can spell correctly. And then the equation is we're going to go back to this. We're going to say f of x equals our n sub 0. Well, we don't have an n sub 0. We have a first term. So if I were to go backwards, I would divide by 2, so that would be 1. Times our common ratio, which is times 2 to the x power. And that would be my answer. I could simplify that and just say 2 to the x. We don't really need this 1. That 1's kind of extra, so we can take that off. All right, so that's how we do these. Like from here, let's look at number 2 here. 66 to 50, well, that's subtracting 16. Ooh, but what is that in multiplication? Right? What do I have to multiply 66 by to get 50? Right? What do I have to multiply 66 by? So some ratio equals 50. Well, I can find that ratio if I divide both sides by 66. So the ratio would be 50 over 66. I have no idea what that is off the top of my head. Ooh, 0.75 forever times 0.75 bar. Let's see what happens. So then I go from 50 to 34. Oh, that's the same as if I subtract 16. So I can see what I'm doing is I'm subtracting 16. This is arithmetic. Okay. So 18 minus 16 would be 2. Minus 16 would be negative 14. Minus 16 would be negative 30. Minus 16 would be negative 46. And so my equation is f of x equals my n sub 0, and once again I have the first term, not the 0th term. So if I were to go backwards and put 16 on top of that, I would have 82, and then I add, whoops, I don't add, I subtract 16 for every x. And so that would be my equation. Never mind the squiggling out of the subtract or the addition sign there. And so that's what we're doing for each of these. Okay. So now it wants us to use the graph to find the values. So the tricky thing here is when it says f of 2, well, typically we write f of x. So f of 2 means when x equals 2, y equals blank. So when x equals 2 is this line here. So what is our y value? It's right there. So likewise, when it says when f of x equals 4, that means we're trying to find x. So when f of x equals 4 is right here. So what is our x value? Whatever that is. Okay. And so that's what you need to look out for. f of x means what is the x, f of 2 means what is the y. So keep that in mind as you do this page. Okay, so now we're doing a little bit of what we did in class today. So I'll zoom in for this one if I need you a little bit closer detail. All right, so it tells us what the growth is, and it tells us the growth in the table is triple at each whole year. So the growth is triple, and we can see that very clearly. The 2 times 3 is 6, so that means we're going to times 3 here to get 18, which means we're going to get times 3 here, which would be, I don't know that off the top of my head, 18 times 3 is 54, and then we do that one more time, times 3, 162. Beautiful. All righty. Cool. But now we need to factor it, right? So now what we're looking at is we're looking at each half step. I'm multiplying 2 times some number, then times that same number again to get 6. I'm going to call this number f for the sake of argument. So look at what's actually happening here. To get from 2 to 6, what I'm saying is 2 tripled is 6, right? I'm saying 2 tripled is 6. But when I look at the factors here, what I'm saying is 2 times f times another f equals 6. So let's just follow this through its logical conclusion. That means that's the same as 2 times f squared equals 6, which means f squared equals 3, because if I divide by 2 each time I get 3. So that means f is the square root of 3. So I know that each of these little functions I'm doing the square root of 3. So that this is actually 2 times the square root of 3. And then if I multiply by another square root of 3, that would give me 6. This is going to be 6 times the square root of 3. If I multiply by another square root of 3, I get 18. This is going to be 18 times the square root of 3, etc., etc. Okay. 13 is very much the same thing. The growth is tripled. So we see we have the exact same thing, except this time, instead of doing 1, 2 to get there, see here, it's still times 3. This time what we're doing is we're doing 1, 2, 3 factors. 1, 2, 3 factors. So I know that 2 times f cubed is supposed to equal 6. So when I divide by 2, I have f cubed equals 3. So f equals the cubed root of 3. Whoops, that is cubed root of 3. So this is going to be 2 times the cubed root of 3. And now this one's interesting too, because what I have here essentially is I have 2 times the cubed root of 3 times the cubed root of 3. Okay, so I have those two things happening. Whoops, let me put that on the camera. 2 times the square root of 3, or cubed root of 3 times the cubed root of 3. So when we have two things that are cubed roots, we just multiply what's underneath. So we have 2 times the cubed root of 9. 2 times the cubed root of 9. And so here's what I actually want to show you guys. So you see that this is to the 2/3. So what this is this is being raised, 3 is being raised to the 2/3 power, right? So what's happening here, what's really happening here, is we have 2 times 3, not once, but 2/3 of the time, okay? So we're raising it to the 2/3 power. So what does that mean? Well, that 3 becomes a radical, and the 2 stays the way it is. So what this means is, we're going to do this denominator first. We're going to say 2 cubed root of 3 squared, which is 2 cubed root of 9, which is exactly what I did there. That's kind of the cool thing that's happening here with these fractional exponents. For example, let's just pick another number at random. Like if I were to raise, 3 to the 3/4 power. This would be the same as the 4th root of 3 cubed, which would be the 4th root. 3 times 3 is 9 times 3 is 27 of 27. Okay. That denominator becomes the root, and the numerator stays with it, and then we eventually just evaluate that, however it is. Not necessary to do this, you just kind of need to see the patterns, but I think it's certainly helpful in getting us there. 14 is interesting because it does halves, but you kind of have to fill in a couple more there. Finally, our go section asks us to simplify these. So the rule when we have exponents is you could evaluate this out. You could do 3 squared, you could do 3 to the 5th power, and then multiply those numbers together. But it wants us to write the answer in exponential form, which means 2 squared plus 2 to the times 2 to the 5th equals 2 to the 7th. So if we have the same base, we just add our exponents. So this is going to be the same as 3 to the 2 plus 5th power, or 3 to the 7th. Now why is that true? Well, what does 3 squared mean? 3 squared means 3 times 3. And what does 3 to the 5th mean? 3 times 3 times 3 times 3 times 3, and then we're multiplying these together. So in fact what I have is 1, 2, 3, 4, 5, 6, 7 3's multiplying by each other, or 3 to the 7th. Now when we divide, it's the opposite, right? Since we added here, this is going to be the same as 5 to the 3 minus 2, or 5 to the 1st power. Why is that true? Well, let's look at what's actually happening here. This is 5 times 5 times 5, all over 5 times 5. And the rules of fractions means that these cancel out and these cancel out, leaving us with just 1 5. 17, 2 to the negative 5th. What does it mean to raise something to the negative power? That's the inverse. So this is going to be the same as 1 over 2 to the 5th. 1 over 2 to the 5th. Okay. And so with those basic rules, you should be able to do the rest of them. Well, anything to the 0 power is just 1, so you should know that one. 19 you should be able to do. 20 is a little bit complicated because we have this negative 2 here first. So my first move with that is we can do all sorts of things, but just remember this here. When we have them multiplied by each other, we add. So this is going to be 3 to the negative 2 plus 5, all over 3 to the 7. Negative 2 plus 5 is going to be 3 to the 3 over 3 to the 7. Then, from division, we subtract. So we have 3 to the 3 minus 7. Whoops, I didn't realize I was off the screen there. 3 to the 3 minus 7, which is going to be 3 to the negative 4. And then because of inverse rules, you should be able to answer it from there. There's just one more step you need to take. All right, guys. That's tonight's homework. Good luck with that. Come ready tomorrow. Remember, this is hard stuff. This is challenging stuff, so just kind of keep an open mind about it. Work on that mathematical brain. We're trying to make those connections, and we want to be able to explain things, and we want to be able to ask meaningful questions. So come to me tomorrow, ready to do that, and we'll continue to build on this. Have a good day.